Hello everyone. Welcome to Linux Forensics here at Pentester Academy. In this video, we're going to run the Python script we developed in an earlier video. So we added superblock information together with the group descriptor information, and we were able to come up with a little bit better picture of how things look. So here I am at my command prompt, and if I go ahead and I run xfs.py on media, fill, Toshiba, disk images, 2015 3.9 IMG with an offset of 2048, and I'm going to go ahead and pipe this to more, we will see my super block. And here's all the features it has. It has a journal, not surprising. It's ext4. It has extended attributes, resize inodes, and directory indexes. So if I hit space, I can see its incompatible features are file type extents, which we'll talk about in later videos, flexible block groups. I see for read-only compatible features, I have sparse super, large file, huge file, group descriptor table checksums, directory end link, and extra I size. So I have several features there. I hit more. I can see some other interesting information. It was cleanly unmounted. Here's the UUID and the time it was last written. Now I go through my different block groups. Block group 0 has the inode zeroed flag, and its blocks 0 through 32K, and inodes 1 through 8K. Naturally, as the first group, it has a super block, a group descriptor table, and it has a whopping 1K of reserved blocks. And why is this? That's because normally the file system has to be able to expand to 1024 of its original size. So if I needed one block, now I need 1024 blocks. After that, I have my data block bitmap, my inode bitmap, and you might notice there's a big gap here. And I have my inode table. Once again, there's a big gap, and then there's a huge gap to the data blocks. Well, why is that? We talked about flexible block groups earlier, and this is being used on the system. So since I have flexible block groups, what that means is that all of that information is in the first block group in my flexible group. Now in this case, the group size is 16. So I have 16 bitmaps. Notice this is 16 blocks, and it's 16 blocks from here to here. And then my inode table is roughly 512 blocks, and that times 16 is where I get this huge gap. So notice that I'm displaying this information because this is where the information for this particular block group is. It's in the descriptor, but some of this stuff might not actually be in this particular block group. It is in this case, but if we go to the next block group, that won't be the case at all. So here in block group 1, I have my inode zeroed flag. Here are the blocks, and here are the inodes from 8K to 16K. And once again, I have a super block and group descriptor table. And why do I have that? I have these because recall that the second block in that group has a backup. So I have a backup of these items, and then these items here are clearly not in this group. They are clearly inside of the first group. And if I go along, I will see in group 2, there is no superblock, etc. In fact, the only thing in group 2 is data. You can see that this corresponds to this guy here. It's all data blocks. If I look at group 3 is a power of 3. So because of that, it has a superblock and group descriptor tables, etc. So it has less space available for actual real-life data. Then I go to group 4. It has just data. Group 5, it's got a backup. It's power of 5, etc. 6, just data. 7 is a power of 7. And I can keep going here, and I will see that most of these blocks do not have a super block, etc. in them. So if I get to 25, 25 is power of 5. So I do have a backup. So you can see that our little script works. And again, it does give you some information that is not given to you by the sleuth kit. And we now have some Python code and some Python classes that we can reuse later for some other things. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon.